Lesson 107, margin of errors again. This time, if we're measuring a mean, like the mean weight of koala bears or whatever, or, mean temperatures, whatever. If we're measuring means, you might remember 2 lessons ago, 105, it was for a measured percentage or a measured proportion. It took us 2 more lessons to get to measured means because we had to go through the bell curve. So that's why we stopped, did the bell curve, learned about z-scores and that kind of stuff. We're going to need that stuff here as well. So, part A here says statistics mini reference. Now, you kind of got that already. I'm going to show it to you because I just tacked it on the end of this. This is actually, in terms of number of pages, a short lecture. It's only 2 pages. Here's the statistics mini reference. So, you know what this formula says. It says if you want to find the mean of some numbers, you add them all up and divide by the number of numbers. That's what that says. I even gave you the Excel command. So if you enter all your numbers in a column somewhere, and then you go over to some other cell and type equals, you have to type the equals, and then you type average, the word average, and then you put a parentheses, and then you click on all the cells that have the numbers in them, and then you close, and it'll spit out the average for you. It'll just calculate for you. Try it. You'll like it. Standard deviation is something we're going to need today too. So here's a formula for standard deviation, which we will use, so you'll get to see how that, how does that feel when you use that formula. Please note that this is not the standard deviation. This is the square of the standard deviation. So you're going to have to take the square root in the end. Or you know what else you could do? You could get this stupid thing to stop popping up on me. That's what you could do. Anyway, you could go into Excel, put all your numbers into a column somewhere, and then go somewhere else, click on a cell, type the equals into that cell with stdev.s. You have to have the .s. And then you open up a parentheses, put the range of cells in there, hit equals, and boom, you've got your standard deviation. Try it. You'll like it. If you have a Excel spreadsheet open while you're working on your homework, it's going to make you happy, I think. Let's see. That's just some old binomial distribution stuff. We've seen that before. Remember the old mu equals np, sigma squared of npq. You do the plus or minus 2 sigma rule of thumb for a roughly 95% confidence interval there. There's how you find the probability of exactly x successes and so on. You'll remember we were using this table 2 lectures ago when we were finding margins of errors when measuring a proportion or a percentage. Well, today we're going to be using this different margin of error formula, which is for means. It's got this weird t in it. What's that? Well, let's worry about that later. It comes from a table. S means standard deviation for your sample. N is your sample size. And let's just get going. And then, let me show you the rest of the handout, I suppose. There's your z-scores, which you've actually already played with this table for the last homework. So if you have a z-score, you can look up the area to the left and get a probability out of that. And then this is something called the student t distribution. This, by the way, is that t alpha over 2 that you saw in that formula. This is the table for that stuff. So I'll show you how to use this table in context when we get to an example. So what do you say we get to an example? I think I've got, how many examples I got? Well, I got like 2 big ones split up into 4 examples. Here we go. Quincy, the QC technician, takes a sample from the assembly line. 10 widgets. 10 widgets off the assembly line, not 10 in a row, not every other one or anything, but 10 sampled completely randomly. Anyway, they have a mean weight of 148.4 grams. Okay, let's get some nomenclature or whatever going right away. That's the mean weight of a sample. You use an xbar, the mean for a sample. By the way, this mu that we used to use for a mean refers to all of the universe. The whole universe, okay? So in other words, we're talking about widgets here. Stop doing that. We're talking about widgets here. All the widgets in the universe, the mean of those, the mean weight of those, you would use a mu to refer to the mean weight of all the widgets in the universe. But just the ones that are in your sample, when you take a sample of however many and you add them up and divide by the number in your sample and you get a mean, you don't call that mu because that's not for the whole universe. That's just for your sample. So we use an xbar for your sample. Okay, so just keep that in mind. There's two ways to write down mean. One refers to the sample, one refers to the entire universe. So what is his point estimate for the mean weight? Well, again, when you take a sample, that's giving you an idea what the mean would be. Let's see. Well, actually, they told us. We don't even have to calculate. They told us. They have a mean weight of 148.4 grams. Boom. That is the point estimate for the mean weight of widgets coming off the line. What does this sentence mean? This is our point estimate. Means it's our best guess, or our best, it's not really a guess. It's our best estimate, I guess. I guess it's not a guess. It's our best estimate. It's our best estimate for the actual true value. What is the mean weight of all widgets that have ever come off this assembly line and ever will come off this assembly line or whatever? That would be called mu. We're trying to figure out what that is. And right now we have an estimate because we took a sample. The sample just gives you an idea. It doesn't give you the final answer. It gives you an idea, right? So that's why we have these two different symbols. Anyway, while I'm at it, while I'm talking xbars and mu's here, I might as well point out, maybe in a different color to distinguish this, PS, S is the standard deviation of the sample, and they're telling us 1.25 grams, standard deviation of 1.25 grams. Sigma would refer to the population beyond the sample, including beyond the sample and beyond the sample, which is what I was saying before when I said the whole universe. I'm thinking maybe that was a little dramatic, but we could say it refers to the whole population, even the ones that are not even in the sample. Okay, so S is the standard deviation taken of the sample. You know, you took the sample and you plug those numbers into a standard deviation formula, you get a guess. If you actually knew this, the standard deviation in weights for all of the widgets, then it's beyond the sample and everything, all of them, we would have called that a sigma. Okay, so try to make sure you use the right symbol at the right time. Anywho, shall we get back to calculating some stuff here? So we haven't even calculated anything yet. So what is his point estimate? It's this. Okay, what's his margin of error? You go get that formula from that page. Let me go run and grab it real quick. You ready for some scrolling? Where is it? There it is. Grab that formula. So, got it memorized? All right, come back and use it here. Whoops. E equals, it's this funny thing called T alpha over 2. And then we have S, there's that, the standard deviation of the sample, over the square root of N, which is the sample size, right? So they gave us the S, they gave us the N. What they did not give us was this. This is called student T distribution, and actually it's a critical value of. So T alpha over 2 is the critical value of the student T distribution. Keep in mind, please, that this is all one symbol, one number. You don't plug like alpha in or something weird like that. No. This is T alpha over 2 is just a big fancy name for this one number. Where do you get T alpha over 2? You get it from that table at the end. Look up T alpha over 2 in table. Using, now the sample size was, what was the sample size anyway? There it is, 10 widgets. He sampled 10 widgets. Just for giggles, that's called the degrees of freedom. I don't need you to know that, but just so you know, if anyone ever says degrees of freedom, that's what they mean. So you take the sample size and you have to actually subtract 1. So the sample size was 10. Don't forget to subtract 1. We're going to use 9. And then you have to also use the confidence level, 95% confidence level. So let's go get it. So remember these two numbers. we have n minus 1 is 9. We have a 95% confidence level. To the end. Scroll time. All the way to the end. There we are. The n minus 1 was 9. We're somewhere in this row. And we were using a 95% confidence level. So we're somewhere in this column, right? So that means we're right there. 2.262. That's our value. 2.262. Come on back up with a 2.262. Where were we? There we are. 2.262. So that just comes from a table. So now back to our calculation, back to blue, I guess. E is take the T alpha over 2. I'm looking at this formula now. Take the T alpha over 2, which is a 2.262. Multiply it by, take the S, which they told us was 1.25 grams, right? That was just stated up here someplace. And divide that by the square root of the sample size. Now the sample was 10, so by the square root of 10. Now make sure you punch your buttons very carefully and get the same thing as me. I've noticed some people in the homework, they write down all the correct numbers here and then somehow their E doesn't come out right. So make sure you're pushing buttons in the correct order and all that. You should match me exactly. I got 0.8941 grams. That is the margin of error. That is the answer to part B. And we're almost done with this one. Write the results as a confidence interval. So you remember this idea. Maybe I'll go to green now. You do the old, you figure that the true value of the mean is somewhere between what you measured in the sample plus or minus the margin of error. So in other words, what was our measured value? It was 148.4, says it right there. And we're going to add and subtract this, what, 0.8941? Maybe I could just say 0.89, huh? Yeah, I guess that's what I did. I'm just looking at my, come on, you. Man, these things. 0.8941. And so if you go 148.4 and you subtract that, you're going to get something like a 147.5. I don't want to show more decimal places than this has. So something like 147.5 on the low end, and on the high end, 148.4. Add that, you're getting something like a 149.3. And remember to state your confidence level. Okay, there's our answer. I'm going to get out the red now, or the pinkish anyway. Must state the confidence level. It is, again, I said this 2 lectures ago, but this would be a meaningless statement if you didn't say, well, what's your confidence level? Because remember, different confidence levels are going to give you different, you're going to add or subtract different. Well, what's going to change is this multiplier here. So it changes your error, your margin of error directly, which means, of course, it's changing how much you're adding or subtracting directly. So if you have no idea what the confidence level is, then you have no idea how to interpret these numbers or even where they came from. You don't know. So make sure you state the confidence level. So this is saying, yeah, we're going to come out somewhere between 147.5 and 149.3, and if that's acceptable for whoever's in charge of the production line, then you're good. And if it's not, I guess you got to freeze the assembly line and start over. Oh well. Example 2. Quincy again. What would be the effect on his margin of error if he increased his sample size? Well, basically, bigger sample. Well, let's look at the margin of error formula. It goes like this. T alpha over 2 S over square root of n, right? So a bigger sample makes this bigger, makes E smaller. But remember, there's also an effect in the T when you go looking up the T as well. Let's just take a quick look at our table at the end again. Okay, so as the sample size goes up in this direction, notice it doesn't matter which column you're in, these are all going down. Your T values here are going down. They get smaller. As n gets bigger, your T values get smaller. So come on back up. Let's include that in our consideration here. Also gets smaller. So making E smaller. So there you have it. They both tend to make E smaller. So if n is bigger, that directly influences your value right here and makes your E smaller. But it also makes this value smaller, which makes your E smaller. So I think I conclude it gets smaller. Smaller. It gets smaller. Okay. Let's see what this other question says. What would be the effect on his margin of error if he raised his confidence level? Okay. Do you remember what this did a couple lectures ago? Higher confidence level. What I said before is if you want more confidence in catching the butterfly, which is kind of like catching the true answer, you want to give an interval and you want to say the real answer is somewhere in that interval. You want to have a better chance of catching it in that interval, make a bigger interval. So you want a bigger interval. You want a higher confidence, you want a bigger interval, which means a bigger margin of error. That's what you want. Now, can we show that that's really what's going to happen? Raised his confidence level. Well, again, that came in on that table at the very end. So once more, I'm going to have to scroll to the end. Hold on to your horses. What happened? Ooh, you got to really hold on to your horses there. Okay, so you come back to the end here, right? If you want higher confidence, notice that's going this way. And in any one of these rows, doesn't matter which one, as you go this way, these numbers are getting bigger. So the E gets bigger. T alpha over 2 gets bigger. Ooh, where'd it go? As confidence level goes up, so does your value of T alpha over 2 that you look up, which means so does your margin of error from the formula, which means same thing, bigger interval. Here's your answer right there. Higher confidence, bigger interval. Higher sample size, smaller interval. Okay, so you can monkey around with confidence levels, and especially sample size is something you're allowed to mess around with sample size all you want. But if you want to be more confident, well, use a bigger sample. Wow, I finished page 1 already. Okay, well, this is our nice big example, the full example. We're going to start from the very beginning. We're going to pretend this is really the real world. And what we got here, you can read the problem, but what we got here is 4 temperatures that we've measured. We've measured 4 temperatures in an oven when we set the knob somewhere. Based on this data, what's the best we can conclude about the true temperature? See, these numbers were all measured when the dial was set to 350. So the dial was set to 350. Look at these temperatures, 385, 390, 382, 388. They seem higher than 350. Knob must be broken. But anyway, the question is, when it's set to 350, what is the temperature? We need to have an estimate. What is the temperature when we set the dial to 350? So what that basically means is we want to find some kind of a mean here. What is the mean of all these temperatures? Now, you could get a point estimate. So the mean is, you would add up all the temperatures, 385 plus 390 plus 382 plus 388, and then you would divide by, well, there's 4 of them, so you divide by 4, and I worked this out, and what did I get? Boink. I got, what did I get? Where are you? There it is. I got 386.25 degrees Fahrenheit. That is not the true mean. In other words, if we kept measuring these temperatures for like a long time and got a mean, that's what mu would stand for. But we're not measuring the temperatures for a long time and getting the mean. We just measured 4 of them and get the mean. So it's definitely just a little sample, and that's why we use an xbar instead of a mu. Okay, so we expect it somewhere around 386.25. What we're really interested in is how far off is that? What is the margin of error? Well, remember, there's a formula for the margin of error that goes like this. We're going to be looking up a critical t value in a little bit. And then this is the measured standard deviation, or I should say standard deviation of our sample over square root of sample size. Okay, what do you say we maybe look this up first? So you have to know two things. You have to know the n minus 1. N is the sample size, 1, 2, 3, 4. Minus 1 is 3. And then the confidence level we want to look for is, does it say? It doesn't give us a specific confidence level, but we'll use 95%. Because that's generally what you use for something that's not medical or something, 95%. So n minus 1 is 3, 95% confidence. Hit the table, scroll in again. Okay, n minus 1 is 3. What do you say we get rid of this stuff? N minus 1 is 3. Remember, n is 4, so we look up in the 3. N minus 1 is 3. See, it's labeled n minus 1. N minus 1 is 3. And then did we say 90? Yeah, we chose 95% confidence. So that one, 3.182. That's our critical T. Scroll on back up. We're going to use, what did I just say? I just said, what did I just say? What did I just say? Darn. What did I just say? 3.182. That's what I just said. 3.182. Okay, that's what we'll be plugging in there. N is the sample size. We're going to have to stop and get S for a minute here. So now I need that formula for S, which is down here. I have to go, there it is. This thing. Okay, that formula says S squared is, now that's a summation symbol, and what we're summing is a bunch of squared things. And then that's going over n minus 1 like this. Okay, this means add. This means add all of these things. What are these things? Well, they're in parentheses. So you take x. What's x? These are our x's. That's an x, that's an x, that's an x, that's an x. So we take the first x, 385, and we subtract the x bar, 386.25, close the parentheses and square it. So again, this says we're going to add it up. We're going to visit every data point and do the same thing. So now I come to this one. I've got a 390 minus a 386.25, close the parentheses, squared. And I'm still in the numerator here. I got to visit the next data point, 382. 382 minus x bar is 386.25, close the parentheses, squared. And then I have to visit the last data point, 388. And minus the mean, the x bar, 386.25, close it, squared. That's all added up on top. Divided by n minus 1. Well, n is 4, so 4 minus 1. If you don't mind, I'll just write a 3. So you come up with s squared equals, and you got to be very careful adding that stuff all up. I ended up getting, well, when I just did this part, I ended up with a 36.9275, and that's being divided by 3. Now remember, we want to take the square root of that stuff. Square root of that stuff. And that came out to a measured, or I should say a sample value of standard deviation of 3.508 degrees Fahrenheit. That's our S. Why did we need the S? We needed the S because it's in our error bar formula. Okay, what do you say we go to a new color and continue right along here? So, E equals the T alpha over 2. We looked it up. Remember, that's based on sample size and confidence level. Times the S, 3.508, that we just calculated, and divided by square root of sample size, which was 4. Okay. And make sure you plug your stuff in carefully. Make sure you get exactly the same result as me. I'm getting here. E is equal to 5.581, and this would all be degrees Fahrenheit. That's the margin of error. So we measured a mean of 386, and here we're saying that the margin of error is like 5.5 degrees. So to be all official about it, let's assemble our answer. So the mean temperature is what we measured for our sample within a certain margin of error. we're going to have a 386.25. That's what we measured for our mean for the sample of 4. And we're going to add or subtract to that our margin of error of 5.581. And when you do that, and when you maybe round off to maybe 1 decimal place or something, I'm getting on the low end just about 380.7. Remember, mu, that's like the real answer is what that is. X-bar is just, well, you know, we took a sample. But mu is like, we think the real answer is somewhere nearer to what our sample says. Somewhere between 380.7 and 391.8. And this would all be degrees Fahrenheit. Please remember to put your confidence level here. It's extremely important because it wasn't even saying what confidence level to use. You had to choose 95%. By the way, if it doesn't ask you for one, you're probably going to choose 95%. It's a good rule of thumb. But there we go. So now you can sample things. You can measure the weight of 4 bolts, whatever, and you can put an error bar on your measurement. It's a wonderful thing. Of course, you're going to have to state a confidence level. You're going to have to use that special T-chart, but it can be done, and it's really not bad. It's rather cookbooky, isn't it? Okay, believe it or not, that finishes our introduction, or what should I say? Our first unit, which is where we were doing some QC tech statistics type stuff. We'll be doing trig next, but that's next.